Yes, I tried that.
working.
Yeah, first. I know it's working. Okay. There. Anyway, first of all, I think most of you know where Dartmouth is. So it's north of us in New Hampshire. And it's one of the 7 or so Ivy League schools, smallest, most northern one. Yeah, I usually show this slide when giving a talk in Norway, for example, when people have no idea. Some pictures of my group over the years. I tend to keep a very small research group at Dartmouth. And you'll see that obviously some of these faces are photoshopped in. And then I ran out of room in my original photo, and so I took a new photo recently of my current group. Okay, so where do we start on the image sensor story? And I want to start in the mid-60s with kind of 2 innovators. One is Gene Weckler, was at Fairchild, and Gene was the first one to figure out that rather than measuring the instantaneous photocurrent in a diode, which is very, very tiny and very prone to a lot of noise, that you could actually use the capacitance, the self-capacitance of the p-n junction as an integrating capacitor. And so all you have to do was to close the switch, reset the diode to something, and then let it float. And then the photocurrent will accumulate on the capacitance of the photodiode. And that gives you some gain that allows you to make a much better quality imaging measurements. And then just a year or so later, Peter Noble at Plessey actually thought that, okay, well, we've got some voltage. Or this way, I just can't see. Some voltage, and we want to read that out. So maybe we could put an amplifier in the pixel. So we put a voltage follower or source follower transistor in the circuit. And that was really the first active pixel sensor that was made. And they built an array of 10 by 10 diodes of this. So, and that was in 66, 67. And there were a lot of issues at that time. For example, process technology was pretty primitive. And not only was the process primitive, but the understanding of process technology was primitive. I remember him telling me that they would grow oxides in the furnace to grow for the MOS devices. And then during lunch, the technical crew would put their sandwiches in the same oven to warm them up for lunch. So there might have been some contamination issues there. So there's a reliability, instability issues with that MOS device, and then some circuit issues as well. But still, they were able to see light, and he was able to make a very primitive camera using that 10 by 10 or even larger array. That was in 67, but so it was the beginning. But unfortunately, for that technology, the CCD, charge coupled device, was invented just in 1969 by Boyle and Smith at Bell Labs, trying to find an electronic analog for magnetic memory bubble memory. It's redundant. And the way that device works is it uses an MOS device in non-equilibrium. So you can have packets of charge stored underneath electrodes, which is shown on the left-hand side here, running vertically, then a cross section. And as you apply different voltages on the different gates, you create different potentials in the semiconductor, which can attract electrons. And by applying these voltages in sequence, you can actually move these packages of electrons through the semiconductor and get them to travel in a very stepwise sort of digital timing fashion. So you can build an array by building a lot of these shift registers vertically, shown in the green part there, and then slowly move charge after it's been integrated in the CCD potential well from light, move it down towards a register that's down at the bottom. So you imagine that you take one step down with all these columns in parallel, and the very charge at the bottom, the last charge, goes into this blue shift register at the bottom. And then quick like a bunny, you shift all that charge to the right out to an output amplifier where you can read out what the value of each charge packet is. Then you shift the next row set of columns downward one step and repeat that process. So slowly but surely, you can read out every single charge packet in the array. And it all goes through one common output amplifier, which is very convenient because then you don't have any non-uniformities or mismatches between pixels. So Boyle Smith were recognized for that by the Nobel Prize in physics, actually, because astronomers used the CCD for astronomy applications and thought that the inventors of that technology should be acknowledged. But there is no Nobel Prize in engineering. Oh, see, I'm misspeaking. It's already, just remember, it's 2 o'clock in the morning. There's no Nobel Prize in engineering, so they got the physics Nobel Prize. And the citation was for the invention of the CMOS image sensor. Oh, wow. That's embarrassing. CCD image sensor. So Mike Thomset, who actually is the sole inventor on the CCD image sensor, was left off of that prize. So, which was an unfortunate decision by the Nobel Prize committee to write that citation. Boyle Smith Seltzer deserved the Nobel for the invention of the CCD, but the citation came wrong, and poor Mike was left out. Okay, so that's around 1970. And you may wonder, what about Fawcett? What was he doing in 1970? So here I am on the left-hand side. By the way, at the Talcott Mountain Science Center, studying balloon and airflow over the Talcott Mountain. So I was obviously not involved with image sensors at that time. But CCD's cameras were developed then based on that technology over the next 2 decades. And there's a couple of images of different CCD cameras, but maybe center top is one of the most impactful ones, is Steve Sasson with the first digital, self-contained digital camera that he invented at Kodak, which for him was kind of an under-the-table project. He was interested in learning about CCDs and then thought he could maybe build this contraption. When he showed it to Kodak management, the response was pretty famous. It was like, we don't care about that. Whoa, who want that? We're a chemical company. And they sent Steve away. And fortunately, he wrote up all the things he thought about in inventing that camera. And Kodak got a lot of patents, which later they monetized because everybody else in the world was building digital cameras using that same concepts. Also, there's like the Sony camcorder, which came out later in that period, which many of us remember. And just to remind you that it was a pretty good size camera, and it had a battery like the size of a brick in the back, which would run for about 20 minutes before the battery wore out. But pretty handy for home movies and things, with vacation shots and that sort of thing. But that was the state of the art at that time. Same time I was at Yale by then, working on my PhD. And for those of you who don't know, on the photo, the thing that I'm working on there is cutting a ruby lith for making a mask. Anyone done that before? I see some of you are laughing. Yeah. Very tedious process for making masks, but that's the way chips were made. At least the masks for making chips were made at that time. And this was a CCD device that I was working on. And I had this idea that I'd like to build a smart image sensor that would take an image like this, the Volkswagen Beetle here that I cartooned in here in my thesis. And you had a lot of array of pixels, and then maybe in parallel, those were connected to pixel processing elements. And you could do on-chip kind of, well, they would call it edge computing these days, by the way, but on-chip processing of an image. And how do you do that processing? Well, I was also working on trying to figure out how to build analog signal processing or analog computing elements with charge packets. And it's pretty easy conceptually to think about, how do you do addition? We just take 2 charge packets and 2 buckets and just combine them together. And that's an addition process. And you can do that with 7 or 8-bit accuracy, or actually even more accuracy than that. But if you want to do subtraction, that's a lot more difficult process to think about, but you can do that also with about 7 or 8-bit accuracy, which is fine for primitive image processing on the focal plane. But that's, you're not going to get really high dynamic range or anything with that, but it could work. And then you can combine these different units together, like a little ALU, arithmetic and logic unit, mostly arithmetic, as part of a small computing device, a little programmable computer. But you just move charge packets around by pulsing the different electrodes, and you can actually do some computation. I'm going to skip that step. So I moved on to Columbia University and had a PhD student that continued his work. And that little charge coupled computer shown in the center there, and which you can barely see. Well, I'm just going to point to it over here. 1, 2, 3, 4. 4 photo detectors that are shared between one charge coupled computer. And you can do kinds of primitive image processing that way. So yay for that. That worked. Didn't go too far because he graduated, and that's the real bane of being a professor, is that your students get to some maximum level of output so good that they reach escape velocity. And unless you carefully plan to teach the other monks how to make wine, you lose the alcohol. So anyway, I also worked on very high-speed CCDs, which were we built some of the fastest CCDs, well, the fastest CCDs in the world, using 2D electron gas CCDs, which I'm not going to really talk to about, except they're going to come into my conclusion in a moment, which is after spending time working on a really interesting problem, how can we make really fast CCDs for signal processing, gigahertz and higher rates? Developed this technology, got it working, and nobody cared in the end. Signal processing, high-speed signal processing was overtaken by digital signal processing at high speed. So all that work, several graduate students, years of work, had no impact, really, ultimately. Painful lesson as I look back on it. So some of the conclusions to this little preamble are that analog signal processing is really hard, especially when you have to invent stuff along the way. It took like 10 years to get from concept to demonstration. And really, the conclusion draws that a few analog designers are a lot slower at making progress than a few thousand digital designers, because digital is so much easier. And while you are busy doing the really hard stuff for analog signal processing, the digital designers are taking full advantage of Moore's law and speed improvements and what other designers have designed, and can combine them in cells and all that kind of thing, and they're just going to pass you like the Autobahn. And it only gets worse these days, because compare that to tens of thousands of coders, or hundreds or million coders, where they can make much faster progress if they don't actually have to build any hardware at all, right? They just code it. They can code it in a couple days. They can use AI. They can code it in a matter of seconds sometimes, and build solutions that, of course, are not power efficient or memory efficient or anything, but still successful. So it's hard. Another thing I learned is that new materials and devices are fun, but it's hard to get acceptance unless it's really compelling, because there's usually all kinds of problems when integrating new materials and new devices. Lots of unexpected issues come up. And so what I was thinking at that time was the best thing to do was to stick silicon and get the ADC onto the CCD chip. So at least we could do focal plane image processing in digital instead of analog on or near the focal plane. Well, about that time, I got a call from NASA Jet Propulsion Lab to see if I could help them out with a CCD problem. And I said, heck yes. I always wanted to work in the space program. I was born like within a week or two of Sputnik going up. And it's been, I grew up with a Apollo program. So wow, I could finally do what I always wanted to do in life, which is be involved in the space program, which I thought I'd never get to. So at that time, NASA needed smaller cameras for smaller interplanetary spacecraft, because Dangle was saying faster, better, cheaper. And how do you take the very large cameras, like the one that you can see next to the arrow tip here, that was on the Cassini mission to Saturn, and you see people down at the bottom, just for size reference. How can we make cameras like that the size, well, literally our metric was the size of a coffee cup. That's what we went around telling everybody. Can we do that? And you know, it's so important to send cameras out on these missions. I just shared one thing that I thought was awesome. Here's Saturn, which I'm sure you've all seen pictures of Saturn before, although it's from the top. And you look down on the pole, and you see this very interesting pattern of the clouds. It's a hexagon, right? You can all see the hexagon, right? Amazing. I mean, we go to Saturn and you see a giant hexagon. Is God playing a joke on us? I mean, kind of interesting. So the physics there, of course, is quite interesting as well. But just you learn stuff just by taking pictures. I don't know the reason why it's a hexagon, by the way, so don't ask. So I was thinking about how to build devices that are more useful for NASA to build small cameras. And I already knew, you know, that there was this Mpixel concept out there. And I'm not going to go through all these things. You can just read them quickly yourself. But I wrote a very provocative paper in 1993 about our CCD's dinosaurs, which I didn't make any friends writing the paper because all my friends were in the CCD business. So they didn't really want to hear about the fact that maybe they were going to be obsolete if they didn't switch. Anyway, in 2025 now, it's very well understood and totally accepted that that's true. In fact, it's very hard to buy a CCD these days. But in 1993, that really wasn't the case. It was a long uphill battle to try to convert people into my way of thinking. And that was really the struggle. The idea to implement that was quite simple and quick. Convincing everybody that that was the right path to go on. That was the hard part. So just two devices. The top device was in that paper, which is device that actually was used pretty much like that for the next 10 years or something like that, a little modification on the gate. And then the bottom device was another device that I put into that paper where you can actually move the charge back and forth in the CCD well and resample the charge packet multiple times. So you can, every read has some noise, and you could average out that noise over many read cycles and reduce the noise. And this has actually become, I should say that there was a CCD device that did something similar called this, that's a long story, called the skipper chip for short. And then I just tried to do the same thing in CMOS, but it's become quite popular in search for dark matter and other things, new habitable worlds, to be able to resample the charge and get down to read noise. That's the variation, right, from measurement to measurement. So the read noise is at the sub-electron level. And then you feel like you're really kind of practically counting electrons. Okay. So really, in essence, what we did at JPL in the invention was to try to combine the best features of that 3-transistor active pixel sensor that I talked about that Peter Noble did in 1960s. And then what we learned about CCDs to get very low noise and high performance that, of course, the science community will want in a camera that goes out into space. And so that was that invention of the CMOS active pixel image sensor with interpixel charge transfer is the what it's called. And the main idea is that you can do correlated double sampling to suppress noise. So here's I'm going to try to get through this. An explanation of what correlated double sampling does. How many people know what correlated double sampling is? Yeah. Okay. Would you like to explain? Yeah, I'm a tired expert. Okay, so if we look at the cartoon that's on the left, so we've got some packet of charge, the red dots that are generated by light, those are the photoelectrons. It's a cartoon, so don't take it too seriously. And then there is an amplifier, that's the blue triangle, that is that source follower, voltage follower thing that had a gain, voltage gain of 1, but a current gain that is much higher than that. And then there's a switch that connects this to a positive voltage rail. And then there's a capacitor underneath. And the problem is if you just connect that switch to the capacitor for, wait a little bit and then open it up. And let's say the voltage rail was 5 volts. When you open the switch, what's the voltage on the capacitor? 5 volts. Wrong. Actually, we don't know what it is. Why is that? This is the learning part. Right? So when you close that switch, of course, the capacitor charges up to 5 volts. But what's really going on is that electrons inside the switch wire have some Brownian motion. And they are flowing up in this diagram, up and down, some random fluctuation. And when you open the switch up, some electrons are going to be stuck on one side of the switch versus the other side, just from that random fluctuation, that Brownian thermal motion. So you never know exactly how much voltage winds up on the capacitor. It's always off by a little bit from the ideal average value. And so this is called KT-C noise, KT for the thermal energy and C for the capacitor. And this is just the basic thing about switches and capacitors. So if you add the charge to this reset thing, you don't really know where you started for the voltage. And when you add the charge, you'll see a change in voltage, but you don't know what how much of it is actually attributed to the electrons. So what we need to do is do two measurements. First of all, we have to measure what the voltage is after the reset. That's the first measurement. And then we have to measure it after we transfer the charge. That's the second measurement. We take the difference of those two and get the actual number of electrons. So just to make it easier to visualize, perhaps, if you go into a deli and you want to buy some potato salad, and the person behind the counter, you'll get mad if you don't do this. They put the container first on the scale, zero it out, and then add the potato salad, and they just charge you for the difference, right, in weight between those two things. That's really what we're doing in this case. All right. This is a time to ask a question if you're. It's not critical knowing what we're doing next, but just in case. Okay, so first, that upper diagram, I knew we wanted to replace that polysilicon gate with something that did not block the light so much. So we wanted to use the pin photodiode that Nobu Teranishi had invented for CCDs in 1982, which gives you complete charge transfer. It gives you better blue response and has higher capacitance. So here we're using it in CCDs, but in order to transfer the charge, you needed a high voltage, like 25 volts, in order to transfer the charge. If we're doing CMOS, 25 volts is death to CMOS circuit, so just short it out. So we worked with Kodak to develop a low voltage process pinned photodiode. So Steve Sassong, digital camera, Kodak punted. We worked with them to develop the first good CMOS image sensors. They didn't really, they didn't ignore it completely this time, but they really failed to fully commercialize that technology as well. They did eventually start manufacturing Kodak CMOS image sensors, but they kind of missed the train, unfortunately. Anyway, in 1993, we built the first array. Took a picture of George Washington on a $1 bill, which is like the easiest thing. We went 28 by 28 pixels, so it had to be something people would recognize. So George Washington is very good for that. That's why George is there. This is my group in 1995. So I want to acknowledge all their contributions. And then got very lucky in 1995. There was a reporter from Business Week who was visiting JPL for other reasons, and kind of finished up early and asked if there was anything else he should see while he was down there at the lab. And someone, luckily for me, pointed him to my lab and said, well, Boston is doing something interesting, maybe you should wander down there. So came down, got very interested in the technology and the promise of that technology, and wound up writing an article. Now, we had just started a company to commercialize the technology right then. I mean, it was my now ex, but my wife at the time. Well, I'll just say ex to be honest, but we're still on good terms, by the way. Yeah, so he's got very interested, wrote an article, and then checked with me about some of the technical details. And I said, Larry, by the way, we just started a company on this. I didn't mention this to you, but is it possible you can mention the company in your article? He's like, oh yeah, sure, I can do that. And this is like, you'd have to pay, you couldn't even get this kind of publicity for a startup company, really, even if you paid big money for it. So it was really very helpful to us. And I think any of you that have ever started a company and that was successful realize how important luck and timing has to do with your success, which is something you can't control, and something I try to explain to students, that like, you can do everything right and still get it wrong just because of the timing or something else beyond your control. By the way, the camera in my hand, that little cube camera, was a piece of aluminum that we painted black and drilled a little hole in the front. It's a mock-up. Everybody knew it was a mock-up. No surprise there. But I found this picture of Apple 17 Pro camera modules. That's what's, these 3 cameras on the back side of your camera. And I made it the same scale as the camera that's in my hand. And you can see you get 3 cameras for almost the same size. Today is what we projected could happen if NASA only invested in this technology back in 1995, which they did, by the way. So anyway, I tried very hard to get this technology transferred to U.S. industry. I visited Intel and Kodak and Motorola and a bunch of other national semiconductor, Intel, I said that already. And everybody was interested. They thought it was cool, and nobody thought it would wind up on their roadmap. And that was really too bad, because this was a chance for U.S. industry to actually catch up to the Japanese image sensor market or industry, because we had all the CMOS capability in this country. And it would have been really easy at that time to suddenly overtake the Japanese as far as their CCD production to replace it with CMOS image sensors, but nobody wanted to buy it on that one. So we decided, okay, if no one's going to take care of our baby, we better do it ourselves, because we all believed in it pretty strongly. So we started a company called Photobit in 1995, and Sabrina was the CEO. I stayed at JPL because one of us had to keep our daytime job, because we also had 2 small kids at the time. So we founded it also with Nick Dudamopoulos and Bob Nixon. It took about a year, and then I left my day job at JPL and joined the company full-time as well. From 1995 to 2001, the company grew about 135 people, self-funded, no VC funding at all. Got a lot of investment from strategic business partners, filed 100 new patents or so. I call it perspiration phase. We developed a lot of custom products for people, like the pill camera. So if you know the pill camera, that Israeli scientists came to us and said, hey, we've got this great idea for this medical device, but we don't have a sensor that goes in there, because the CCD just eats too much power. the battery will wear out before. I should say the battery will poop out. I don't know. Anyway, this is why I need to edit these talks. Another application was in the lower center there, the green was our dental X-ray sensors. Company came to us and said, we have this idea about putting sensors in people's mouths, and I think that this technology will work. And I argued with him and said, if it's not going to be good, and he convinced me that it would be good, and of course he was right. Then also web cameras also became popular, and on the right, of course, is the killer app that emerged around the end of the 1990s, cell phone application. So here's the company in about year 2000, and as I mentioned on the slide, in 2001, the Photobit was acquired by Micron Technology, because basically, Sri and I both knew that this company had to scale really fast, because there's going to be a lot of competitors out there, and neither of us could figure out how we're going to do that, and it just seemed better to sell now to a place like Micron and move on. Actually, I stayed with Micron for about a year, and it was a very challenging year because all of a sudden, well, for one thing, I wasn't the boss anymore. And second of all, the people that were telling us what to do didn't know as much about the industry as we'd already learned by that time. So my recommendation is basically, when you do your startup company and you get bought, exit stage left immediately. Don't hang out thinking that you're going to help, because they're not going to listen to you anyway. Yeah. So, all right. Fast forward 30 years, technology has an adult life of its own now, thanks to thousands of engineers across the planet that are now working on this technology. Caltech wound up licensing the patents to all the major players. We had an exclusive license at Photobit to the technology, but then when Micron acquired us, they released that patent IP back to Caltech, and then Caltech went out and licensed it to lots of other people. There's about 6 to 7 billion cameras manufactured each year, not in total, by the way, Steve, it's each year. It's amazing. And if you count what that is, or figure out what that is per second, it's like hundreds of cameras per second. It's like if you had a conveyor belt, one factory and conveyor belt, and the cameras going by so fast that it would be a blur. Couldn't even see them. And as I like to tell my students, that also means that somewhere there's another conveyor belt. It's the same number of cameras are going to landfill, which is also frightening. Anyway, and the semiconductor sales of CMOS image sensors now is estimated to be about $30 billion per year. And the most important one is NASA's finally adopted the technology for use in space. NASA has to be one of the slowest adopters of new technology out there. But in when the Mars Perseverance rover landed on Mars, you really fulfilled our promise for space applications. That lander had about 20 CMOS cameras on it in total, looking up at the parachute, looking down at the lander, other instruments on the lander, and even the small helicopter had a little CMOS camera in it. It was small enough to fly in that rarefied atmosphere of Mars with that little helicopter. So, yay. But new technology always brings new social issues, and the CMOS image sensor technology is nothing different about that. So there's always the concern with cameras about privacy. I really enjoy my privacy. I'm sure you all do too. And yet we also really like to have security. So you get this tension, like when the Boston Marathon bombing happened, that the reason why they caught those guys so fast is so many people had cameras and taking pictures that they were able to quickly identify who the bombers were and then track them down. So, and who doesn't like that idea? So there's always this tension. Personal liberty is another thing that kind of goes along with privacy. But you know, with smart glasses, like the new Meta glasses, I mean, it's quite possible and being done on a limited basis so far that not only can you have a smart glasses with a camera in it and see people, but you can use a lot of facial recognition techniques and AI to real-time identify who the person is that you're looking at, and whatever information you need to know about that person also pop up on the screen. So I wouldn't like that if I was just out in public and someone's wearing these glasses and dig up all kinds of information on me on an instant basis. But I think if you're law enforcement, being able to have that capability is quite handy. Another thing is stress overload. I think the human psyche is only really designed to absorb so much stress. But when we have this godlike ability to see around the planet, all the stuff that's happening all the time, I think that it's really too much overload. At least for me, there's a tsunami in Japan, for example. Now you can see images from around the world. Basically, it's all bad stuff that's happening. The news hardly shows you good stuff. Body cams is another double-edged sword. If someone accuses the police of doing something unlawful, and the police can roll back the tape and see that actually it was the perpetrator that did something unlawful and the police behaved properly, that's very good for law enforcement. On the other hand, if law enforcement really is doing something that's not so good, it really is good for the person that's being falsely accused or injured. And then the thing that is also incredibly remarkable and good and bad is, I love my drone to fly it around and take nice pictures of my farm, for example. But having lots of small eyes and bombs in the sky in the Ukraine is pretty horrible when you think about this is the face of warfare to come. You just fly around and attack things with first-person vision and drones. So lots of pros and cons. I try to always caution my students that when you're implementing new technology, you should at least think through what the negative consequences of your technology might be. Even though you might be powerless to change that, it's still important. Okay, moving on to happier things. We wound up with, as Steve mentioned, the Queen Elizabeth Prize, and one of those recipients in 2017 was Mike Thompson, who did that CCD image sensor way back when. So he missed the Nobel Prize for physics, but he got essentially the Nobel Prize for engineering. I had a nice, lovely chat with Prince Charles, and I have to say that, boy, he's really good at his job. He can talk to you for 3 to 4 minutes, and you feel like you're the only person in the room. Really chats you up well, seems interested, and then he moves on to the next person. And when you realize he does that every 5 minutes for an entire day, every day, then you start to really feel sorry. But it was a very nice thing. It's very gracious. So, timekeeper, how much time do I have? 10 minutes. 10 minutes, okay. So I'm going to talk about maybe a next generation technology that we have developed at Dartmouth, which is the Quanta Image Sensor, which actually comes in 2 flavors these days: a CMOS image version and a SPAD type. I think I'll just skip this origin part, but let me just say the conceptual idea is that how about in the future image sensor, what if pixels continue to get smaller and smaller and smaller, well below the diffraction limit, and the amount of charge that each pixel can hold also gets smaller and smaller, and then thinking as a good physicist, like, what's the limit here? And the limit is, really tiny pixel that can hold maybe 1 electron or no electrons. That would be the limit. And how do we fix the fact that there's no dynamic range and a 0 or a 1? Well, there is, but very limited. We can replace that with like a billion pixels across the chip and take images at really high speed, so maybe 1,000 frames per second. And then we can kind of take all those ones and zeros and form this artificial construct that I call a cubicle, which is X and Y in time. And then you can use those ones and zeros inside the cubicle to create a grayscale pixel. But now this is all being done in software. Remember what I said about software? People can do all kinds of things. It's like you can have a cubicle size that's very dynamic. So it could depend on the scene that you're imaging. It can be spatially variable as well. You could have some locus of focus, region of interest, where you have lots of detail being calculated, and then areas you don't care about where it just grows detail. You can also have kind of a, attention. You can like just quickly process, see if anything is changing in that area, and then zoom into that area. You can do time delay integration, TDI, because you have, if you can count single photons accurately, then you can do TDI digitally, rather than like a CCD TDI sensor. So the vision I had was like 1 billion pixels readout at 1,000 frames per second, single photon counting capability in each pixel. And by the way, I was inspired by what was happening on cell phones with the other technology I developed. It was like, okay, so let's say it's got to consume less than a watt. So a terabit per second of data collection with billions of pixels for less than a watt. So going to Dartmouth, this was like the fantastic academic project, right? We'll never solve it, but we could keep working on it for years, right? So that's where we started. Let's skip this part. So by now, I think most of you know that, especially in of course you know this, photons arrive not like steady trip. They arrive in a Poisson process. So you can never really figure out what the average light level is until you average a lot of measurements together, and then you can get a sense of what the average light level is. For this type of device, and by the way, so there's an equation for Poisson arrival rate. And for 1-bit quanta image sensor, we only care about 2 states. That is the state where there's no photon arrived, and then the state where at least 1 photon arrived. And it's very easy to write down the simple equations for the probabilities of those 2 things. And then you can calculate what the density of ones are on the image plane for a given average light level. And you see at the very low light levels, the quantum image sensor, the blue curve, is very linear. Well, it's very linear, especially down at very low light levels. And then as the light level increases, the probability, the number of jots or pixels that have been hit, of course, is increasing. And that means the number of jots that could be hit is decreasing. So it takes a while to hit the point where you're actually hit all the pixels on the focal plane with at least 1 photon. So that gives you this kind of saturating behavior, which if you're thinking about a lot of image processing or something, is like terrible. Everybody wants linear response in their image sensors, except photographers. Photographers like a nice saturation. How do I know that? Well, let me replot that same curve on a semi-log plot. And you see that the linear response that we saw before has now become kind of this swoopy thing. That's just because of the graph. And then up in the saturation area, it bends over the other way. So we have this S-shaped curve response. And now, in a feat of historical referencing, 1890, Herder and Driftfield, when they were looking at glass plates emulsions, actually counted the number of exposed granules on the plate as a function of log exposure. And it's the same curve, right? That's pretty obvious here on the here. And why is it the same curve? Well, that's because the way these, where the grains, whatever it is, that's also true for film, they either get hit by a photon. We'll simplify it. They get hit by a photon or they don't get hit by a photon. So it's the same binary process, really. And no wonder that the response is like that. And you get a lot of dynamic range in your image. So that part is pretty cool, I thought. Skip this. This is a signal and noise. And of course, we want very low noise so we can count the number of photons. Yeah, I think I'm going to come back to this, but we can have more than 1 electron in a well today. So it's not the ultimate limit of just holding 1. We can actually have several. as long as we can count the number of photons accurately. Yes. So one way to do photon counting, I already knew way back, would be for SPADs, single photon avalanche detector. But the problems are this requires a very high electric field to get the avalanche. Let's see. Who knows what a SPAD is? Yeah, pretty good. Let me just say you have a high electric field in the semiconductor. One photon is absorbed, generates one photoelectron. The photoelectron then moves to the high field region, gains enough energy that it can actually collide with the lattice and break loose another electron out of its covalent bond. And now you have two electrons. And then there's also a hole that's generated, and it goes the other direction. And it can also then gain energy and hit the lattice and generate another electron hole pair. This thing avalanches, and pretty soon you've got a lot of charge flowing in both directions. And if that SPAD is biased by a capacitor, eventually the voltage across the SPAD drops, and that avalanche process is quenched. But they have to be big devices with high electric fields, because you can't have this thing short out at very large fields. But the good thing is they have essentially no read noise, and because of the high gain bandwidth product, they're very fast at detecting single photons. So I had this idea for how the quiz would work, and I figured out some equations for how the characteristics would look like. And the SPAD groups at the time, even though SPADs still to this day do not meet that requirement of 1 billion pixels per chip, they're not small enough. They're still able to prove that the equations and everything that were there are correct. So I did that first with a SPAD, this group in Edinburgh, which made me sad that I wasn't the first one to experimentally demonstrate this, but I still feel pretty good. So our approach at Dartmouth was slightly different. I'm down to what, 2 minutes now? Yeah, okay, so I'll try to wrap this up soon. Is to detect single electrons by building a really tiny capacitor, just like we talked about before with CMOS image sensors. But if you make the capacitor really tiny, then one electron onto that capacitor creates a voltage that can be above the thermal noise floor. So go for really small, and then you get like a millivolt, or more typically, so far, like half a millivolt with one electron, which you can readily detect. And you can detect with pretty high accuracy. Okay, I'm not going to go through all of this. So we created a new semiconductor device called Gigajot, where you have one electron that's collected in a well. This is a backside illuminated device. The red dominates the electron. There's a transfer gate and floating diffusion. When you are done integrating, you have 0 or 1 or well, maybe 100 electrons in that storage well. You then pulse the transfer gate, and that electron is pulled to the surface. And then you turn off the gate, and the way that semiconductor doping goes is that the electron, instead of going back to where it started from, is actually ejected sideways into the floating diffusion. And that allows us to separate the transfer gate from the diffusion, and there's a lot lower capacitance. So we're able to achieve that ultra low capacitance that we needed. So in 2015, we demonstrated the first quantization of electrons at room temperature with a CMOS type device. And then we improved things over the years. So this is, I don't forget what year this is from, but anyway, it's pretty clear that this is a histogram of signal as a function of light level. And you can see that the photons are very quantized, the photoelectrons are very quantized. And this is photoelectron number on the horizontal axis. This is for 4 different light levels. And if you know the Poisson statistics, you'll see that the peak heights actually are exactly what they're supposed to be for these different light levels and the distribution of peaks. You can go to even more light and still get good separation of peaks. And what this means is that not only can you detect the difference between 0 and 1 electron easily, you can detect the difference, like in here, between 14 and 15 electrons quite accurately. So we can get not only photon counting, we can get photo-electron number as well in this device. So that means that the bit error rates are very low. And I'm gonna skip all this noise stuff. I feel like I just showed that. Okay, I'll show you one interesting thing is that we know what that d log h curve is supposed to look like Werner drift field curve, and with a little bit of noise left in the sensor, you get a little variation from that. And if you fit a curve to those data points that you get, what you find is that if you change your modeling read noise a little bit as you're trying to fit the curve, you can actually estimate the read noise. This may not be important to anybody, but I think it's really cool. You can estimate the read noise, not to just within an electron or two. You can estimate it within a few hundredths of an electron. I'm not sure what it's good for, but it's darn cool. Okay, how do you measure noise down to a few hundredths of an electron? Okay. Yeah, I want to wrap up here before long. So at Dartmouth, we built some experimental chips. This is a 20 different 1 megapixel arrays on a single chip, which we fabricated at TSMC. I always get mixed up between TMSC and TSMC. Anyway, using a cluster parallel readout and a lot of other things, but we were able to achieve 1,040 frames per second with a 0.22 electron RMS read noise. That's enough to be able to detect single electrons accurately. And the total power was about 17 milliwatts of power. So yay for the 1,000 frames per second, yay for the photon counting, and we're off in power by a factor of 17. So, but pretty close, not too bad. So further development required. Able to build a camera that fulfills this promise also, take a picture, in this case of a leopard, and then recreate that leopard through this cubicle computing process. Wound up spinning off a company in 2017 with my two PhD students. And just an example image. I'm down to, I don't want probably negative time, but I'm going to finish really soon. In the lower left picture, sorry, lower right image, is an image that is taken with a 2x2x2 cubicle denoising process. And the average exposure in this image is 0.87 electrons, which we can measure accurately also, by the way. 0.87 electrons per pixel on average. So it's not like we averaged a lot of images together here. It's just a 2x2x2 kind of cubicle. And hopefully you can see that it's a pretty noiseless looking image, relatively speaking. So it just tells you the power of this computational imaging. This is the coder effect, okay? Or lots of people know how to do coding, along with this single photon counting capability. That means we can get really good images in the dark, practically. Obviously, that has to be a couple of photons, but very limited. So this is going to be very good for night vision or other security applications. Very good for astronomy, probably, although they don't want to do the denoising right away, and a lot of other applications as well. So Gigajot went on and built, this is a 0.3 electron read noise device. It's a 4 megapixel sensor. I skipped over the high dynamic range part. You'd be surprised that, oh, you get high dynamic range using single photon counting, but you can. So in the lower right, you get the classic image of looking out through a window and getting images both inside the office and outside at the same time. 16.7 megapixel sensor came next with super low read noise and very decent images at practically no light at all. And then last paper published is a 163 megapixel photon counting image sensor that's operating at room temperature with single photon counting capability. SPADs have also moved along, by the way, they're smaller pixels, and they can also do this as well. So we basically have two technologies now, CMOS image sensor based quiz and SPAD based quiz. SPAD based quiz still has much lower resolution, but has some other benefits, which I can talk about in questions if you like. And as well as the challenges. I should say that here's a challenge that I'm throwing out to people is given this increase in computing capability and deep sub-electron read noise, can we figure out a way between pixel level optics like meta lenses or something like that and computational imaging so that effective pixel pitch scales with the technology node rather than conventional optics laws. So conventional optics says there's no sense building a pixel really below 2 microns practically for an f2.8 system. And yet you can buy sensors today that have like 1 micron pixels or half micron pixels even. So what's going on with the diffraction limit there? Marketing. But I think it should be possible to, between pixel level optics and computing to get us down so we can build 0.1 micron pixels. If we can build 0.1 micron pixels, we can build amazing cameras that are really fit on the head of a pin. So it'd be very important for medical applications, for example, and many other things. So there's the challenge. All of you, I'm still working in the lab at Dartmouth. I still have 4 PhD students, and they are shown here. And then at the end of this talk is a reading list if anybody's interested in some of these things. So I'll leave this up so it's recorded on video for a moment, and then I guess I'm going to end here, and thank you for your kind attention.
Any questions? In the back?
All right. So going back to when you were talking about early 90s, what you did was fairly interesting talk to see the history of the food for sharing. You were talking about that was the first mention you made of like leveraging Moore's law, and you talking about it now to me makes sense looking back. But at that time, I don't know what the foresight of the technology was. Like, did everyone around you believe in Moore's law at that time? As it pertains to your technology development when you were starting into your space, you're putting processing under TCD pixels. Just curious.
And no, there was it was a difficult time actually at that time because I presented this, wrote that paper at an SPIE meeting. I presented it at the image sensor workshop just a few months later. The chair of that meeting challenged me to come up, have a debate on stage about merits of this technology versus CCDs. The first thing he said is, Eric, we worked on this, and he actually worked with Peter Noble at the time. We worked on this in the 60s, and it doesn't work very well. Everybody knows that. Why are you wasting your time on this? So it was fun. I did ask at some point who thought this was a good idea in the audience, and there was at least 3 or 4 people that raised their hand out of 150. So no, it was a long uphill battle. In fact, I feel really good about succeeding at that battle, given the opposition, probably even more so than the invention itself.
David.
Do you see a need to reduce the read noise any further? And is the read noise a problem in your vision where you go to the micron pixels?
Sure, because if you're going to use computational imaging, having a lot of noise along the photons, it's going to make it hard to reconstruct the image. And of course, that was what limited the corrections on the Hubble Space Telescope before they actually fixed the optics up in space. So you could computationally back out the blurring to the bad primary mirror on the Hubble Space Telescope computationally. But unfortunately, you're left with the photon shot noise that would they're kind of limited what you can do. So, yeah, I think it's important to get down to single photon counting with high accuracy and at about 0.15 electrons RMS read noise. It's almost 100% accurate, maybe 3 or 4 or 5 nines accurate.
Go ahead.
Where do you see this going in the next 5 years or so? I think like last year, Canon announced a SPAD camera. I don't know, maybe there are others out there now, and then you see we're going to see both technologies come forward.
Yeah, good question. I mean, well, SPAD is still a big pixel device, which isn't so bad for big scientific cameras. And if you're an optics company, it's probably good too. But if you are trying to build a smaller camera, then big pixels is still a problem. So, and then also SPADs have a problem with power. If they are counting lots of things, then you're charging and recharging that capacitance of that diode many, many times per frame, and that power dissipation actually becomes significant. And the SPAD guys don't agree that this is a big issue with SPAD arrays for a quiz application right now. So I think for some applications, I didn't get to the whole comparison, but I will note that for SPAD quiz devices, you can also do time of flight measurement at the same time, or you can operate both modes. So that's a big advantage. On the CMOS quiz, I think that the technology we've developed and shown so far, and once people thought it was impossible, but once we showed them that it is possible to do single photon counting, I think this technology will find its way into mainstream CMOS image sensors at some point. And devices can be used both ways. So I think both technologies have their strengths. I don't think they're competing head to head at this time, except in certain applications.
So when will your company come out with the product?
I can't tell you that.
Okay.
John?
Can you talk about the power draw and heat dissipation as you increase the density of pixels and the density of devices by a substantial fraction?
Well, as I said, the target was 1 billion pixels at 1,000 frames per second for less than a milliwatt. And very early on, we already hit those, very close to those targets, just within an order of magnitude, which is, by the way, is a small number when it comes to electronics. So of course, if you decide to spend more power on the focal plane, then the power dissipation goes up, and that's not good. That's not good for dark current. It's not good for a lot of other things. So you always want to keep that power dissipation under control, but you can also add coolers if it's a more expensive camera or something to cool it down. I think improvements in packaging have also proceeded pretty quickly, thanks to really high power silicon chips like used for AI and that kind of stuff. So that's another trend that you can just ride along with for free, since you're in a CMOS platform anyway. So yes, you're right. These are all things that we have to consider for every generation of CMOS image sensors and now quanta image sensors. But I don't think there's any fundamental obstacle there.
Back.
How does this technology apply to high-speed cameras? If you can get down to very low numbers of electrons, you can obviously up to frame rate.
Well, there you go. That's the answer. So yes, there's a lot of interest also in high-speed stuff. High-speed usually likes big pixels too. I mean, you're already still limited by light, so you want to have the most light gathering you can do. So probably that would be a case where maybe SPAD at this time is better, because they already have big pixels. And maybe in a high frame rate imaging application, also you have chances to do cooling and other things as well. So camera size usually isn't too much of a problem.
John?
I please see slide number 60. It's one that you mentioned quickly. So this isn't a question. Oh,
Want to see 60?
60. Yes.
Okay, this is not our device. This is generic 3D stacked CMOS image sensor technology. So the top is the micro lenses, you can see, and then there's the pixels, and then with deep trench isolation between the pixels. That's what the orange thing is this volume of silicon in one pixel. And then there's some metallization layers, and then there's the copper bonding pad for hybrid bonding to the next layer. And people actually, this is just 2 layers, but people also have done 3 layers as well.
Thank you.
Stan?
Yeah, so it's interesting work, and when you always talk about moving a lot of the work to software and CMOS circuits. Well, the problem with the CMOS is it stops getting more power efficient about 10 years ago. That's why these data centers are taking it for gigawatt.
Can you speak a little louder, Sam?
Yeah, okay. So I think given that they've got this power limitation, I think there's new opportunities to use either photonics or analog processing to try and get around some of the limitations that are pretty fundamental now in CMOS. So maybe they'll come up with some transistor that's fundamentally different from CMOS that they can get some power savings. But they've been trying that for the last 20 years and they continue to stay with CMOS. It's the basic physics of it is plateaued out, and that's why everything's going to water cooling, and they've got all this power.
Yeah, I mean, I think just one small correction to what you said is that the CMOS used today, even those power hungry digital circuits, is not the CMOS of yesteryear. So really different kinds of transistor, FinFET. Actually, FinFETs are kind of passe too at this point, but and also the technology node is nowhere near where we are with CMOS image sensors. CMOS image sensors were maybe of 65 nanometer, 40 nanometer node. CMOS today using those circuits you're talking about are maybe at a few nanometers node, which is mind blowing to me, but that's where they are. So at least as far as from an image sensor point of view, we have a long runway of technology that we can still lean on before we get to the limits that you're talking about. But you're right. I mean, I'm not saying I know the answer, but it's amazingly how long Moore's law has stayed in effect, given that people thought there'd never be transistors, below 2 microns or something like that.
Fair enough.
This goes back to kind of the history lesson. Could the type of detector be invented earlier? In other words, it did seem like to me that there was a fundamental technological breakthrough that led to the CMOS, the invention of the CMOS device. Like, couldn't they have coupled the photodetector with the VLSI or LSI or whatever those earlier technologies were? Was it really just a mindset thing that people were entrenched in CCD, and as opposed to being a technical innovation that led to it?
Yeah, so maybe it could have, but nobody did.
No.
So, I don't know what to say about that. That's like the obviousness argument that patent examiners make all the time. They explain to them, oh, it's so obvious, how come somebody is important? But people did make CMOS image sensors just before our invention, but they were passive pixel devices or 3T devices, so they had really terrible performance. And they were used in some home security systems and some like Barbie cams, literally Barbie toy cameras. So you could see something, but it was just a crappy image. It was not something that NASA was ever going to use. But they were aiming for cheap and inexpensive. So basically, I figured out how to build a scientific quality device that was also cheap in the end.
Would be that double correlated thing?
It was the putting like a micro CCD into every pixel so that you could do correlated double sampling and complete charge transfer. Yes. And yeah, somebody else could have thought of it. They just didn't.
Go ahead.
Got it. question just about the frame and how it comes out. So you're building the cubicle. So when I think of CMOS sensors, there's some digital value that comes out, there's a conversion gain that converts that to electrons. But for you, you're counting individual photons and then you're summing, I guess, over multiple frames.
Yeah, so the readout is actually just ones and zeros.
Yeah.
Ideally, of electrons, photoelectrons.
For every frame, it's just ones and zeros.
Yeah, it's like the matrix or something.
The matrix.
Very lots of data, like a terabit per second, at least in the ideal scenario.
Like multiple photons.
Well, okay, so then that was a single bit device, and I mentioned some of the multi-bit devices because it turns out you could detect the difference between 100 and 101 photoelectrons. So maybe you should think about using a 7-bit quantizer on the output. And then that gives you some certain advantages. It gets rid of the clean differentiation between grayscale CMOS image sensors and quanta image sensor somewhere in between. But as I said, I think the future for this is this merging of current CMOS image sensor technology with this ability to detect single photoelectrons, or at least get photon number accurately. That's where the fun begins.
Maybe just one follow-up question. So how do you account for physical load in the amplifiers when we were talking about single photon count?
I'm sorry, what load?
Glow, do you have
yeah.
issues with glow where you're maybe detecting, you want to detect from the lines that you actually get some glow from the amplification?
So in principle, it's possible, but that has to do with keeping operating voltages low and keeping currents low at the same time. So the probability of photon emission is nil, almost nil. But it's possible somewhere else you use something that could glow, and then the problem with amp glow is that these infrared photons that are just about the silicon band gap can travel a long way through silicon before they're reabsorbed. And so you get this kind of faint glow from, looks like a heat map, but it's really just the photon glow from some amplifier that is operating over the level that you'd like it to operate at.
Well, Eric, we'd like to thank you for staying up to 3 a.m. I think it's a record certainly for the local section and probably for any kind of national meeting. But again, thank you very much for coming and thank you for giving.
Do something on the floor.